Welcome to the lecture on catalytic organometallics. This is part 4. In the preceding lecture, we introduced the Heck reaction and details of its catalytic cycle. So, the Heck reaction in general, as a general scheme, we have some carbon-centered substrate with a leaving group X and an olefin which might be multiple substituted, but in general Heck reaction are relatively sensitive to steric hindrance. Therefore, olefins with just one substituent react in general faster than those with two substituents or three. Well, palladium 0 catalyst, we need a base, solvent, and HX is eliminated, trapped by the base. Thus we introduce the substituent R to the olefin. As R, we usually have either an aryl group or an alkynyl group. That means in general R is sp2 centered. So the leaving group X is sitting at an sp2 hybridized carbon in general. In principle, it is also possible with alkyl halides, but those examples are rather rare. Simple because then we usually have a hydrogen in beta position, and we will observe the fast reaction of the beta hydride elimination and forming an olefin. So this is somewhat different with, for instance, benzyl bromide, where we don't have in beta position a hydrogen. So it works with benzyl bromide, but not very well, because as we have a base, and you know benzyl bromide is highly reactive to substitution reactions, SN2 or sometimes SN1, mostly SN1, in generally SN1. Well, okay, and therefore the benzyl bromide also is consumed. Yeah? So these are the reasons why we only rarely find Heck reactions with substrates with well, sp3 centered carbon as the site of a reaction. Well, what can be X? Iodide is highly reactive, bromide less reactive, chloride is even less reactive, but meanwhile we have catalytic active systems which indeed allow the Heck-type reactions with aryl chlorides very well. Nowadays, very often, we have triflate as a leaving group, since we could, for instance, transform a phenol to such a triflate. Very nice is the Heck-type reaction with Diazonium salts. Usually this is much faster than the normal Heck reaction, and it has got a name for its own, the Heck-Matsuda reaction. Even carboxylic acids can be applied in Heck-type reactions. In this case, under certain reaction conditions, you form a palladium carboxylate first, which then decarboxylates. So, like that. And now a usual Heck reaction will follow. So as I said, you need some special reaction conditions, then this will also work. What we also talked about in the preceding lecture was that adding in ammonium salts can have some advantages. The explanation we gave was that we will form anionic complexes which are more nucleophilic, and the oxidative addition process to the carbon leaving group bond will proceed faster. And we also discussed some other advantages. In addition, I would like to mention that there are also ligand-free reaction conditions. So, reaction conditions for the Heck reaction without phosphine ligands, for instance, but also with tetra-N-butyl ammonium salts present. The most renowned of those reaction conditions are called Jeffery conditions. You will find details to that in the internet. Also rather nice and easy to set up reaction conditions. However, I think it's still sometimes in question, do we really have homogeneous catalysis, or is that more a case where palladium clusters are formed, which are known that these clusters are stabilized by such ammonium salts. And then the Heck-type reaction would occur on the surface of these clusters. Nevertheless, reaction conditions which very well work. So, here we have seen that the Heck reaction can be accelerated using anionic complexes. On the other hand, it is known that a lot of transition metal catalyzed processes are accelerated or even made possible at all if you use cationic complexes as catalysts, or set up reaction conditions where these cationic complexes can be formed as reactive intermediates. This is also the case for the Heck reaction. For instance, an aryl iodide plus an enol ether, again palladium 0, catalyst and a base. Let's assume that we have standard reaction conditions. We would anticipate to get a mixture of this Heck product and its regioisomer this one. Under standard reaction conditions, we will find this one as the major product and this, on the other hand, as the minor product. Let us change to cationic catalyst. Then it's the other way around. This one minor and this one major. So first of all, let's think about why is this one under normal standard reaction conditions the major product. Well, there is, for instance, the reason that this position is sterically less hindered for the attack of the aryl group. Steric reasons are enough to explain this result. On the other hand, cationic catalytic system, how do we set up this? Well, just add in stoichiometric amounts silver salts, preferentially with counter anions that are non-coordinating or are weakly coordinating. For instance, silver tetrafluoroborate, its PF6 congener, or for instance the triflate. What will happen then? The palladium 0 catalyst, let us assume that it is carrying two ligands, for instance two triphenyl phosphines, will undergo the oxidative addition reaction. That means we will have this palladium 2 intermediate treating it with, for instance, silver tetrafluoroborate, will lead to the formation of silver iodide, which is usually less soluble, and therefore we get to a cationic palladium complex, in this case with the tetrafluoroborate counter anion. Interaction with the nucleophilic enol ether will set up this situation so here the cationic charge mesomerically stabilized by the ether functionality. Well, here I have drawn that with the trans configuration for the next step, the transfer of the aryl group. It should be in cis configuration to that substituent. So it should isomerize if we transfer now the aryl group, well, and I will go on the next blackboard. Well, then we have the aryl group at the position we have, which has been observed as the major product setup. Better hydride elimination will give the observed major product plus this cationic palladium complex, and now we just have to deprotonate the base traps HBF4 and the catalytically active 14 electron palladium 0 complex is formed again and goes into the catalytic cycle again, and this explains also that we need the silver salt in stoichiometric amounts. Another interesting substrate is this dihydrofuran. So, with an aryl halide, again palladium catalyst and a base, what would we anticipate as products the first glimpse? Okay, let's assume the same as here. Well, this or that product, we would assume. Most interestingly, neither nor is formed. So, why? Okay. So, for the formation of this one, we would have the arylation or the carbopalladation at that double bond, in the sense that the aryl group is introduced here, and this is, of course, important. The carbopalladation is always a Syn selective addition process. That means that the aryl group and the palladium is on the same side of the ring. The beta hydride elimination always a Syn elimination, of course, needs then, as I already explained in the preceding lecture, a hydrogen in Syn periplanar position. But the only hydrogen in close proximity is, of course, this one, and it's trans. And therefore, the beta hydride elimination can't take place. So, this system has, therefore, either the opportunity for the retro reaction that doesn't do any harm to, well, the products we might have in focus, or some domino processes might occur, and these might occur as competing reactions in these type of systems. An electrophilic palladium attacks as an electrophile the aryl system. Forming 5-membered pallada cycles. Similar, and then some further reactions would occur. Similar or related domino reactions are very well known at the Norbornene moiety, and we will study that in detail later in this semester. So, for the regio isomer, with the aryl group in 2 position, we need the carbopalladation with this regio selectivity, but again it has also this type of stereo selectivity, racemic, if you don't put in some chiral information, of course. So, and again, to get to this one is not possible just for the same reason as this transformation is not possible, because the hydrogen here is in a trans position. So, beta hydride elimination will occur to this position. So again, this is abbreviated, some additional ligands we will have here. So now, this might dissociate, setting free one product, or a re-addition after internal rotation might occur with a hydrogen at bad position. So re-addition but within the re-addition, of course, the palladium remains on the same side of a ring as the formerly introduced aryl group. Now it could, of course, react back. All those are equilibriums. Or it might eliminate in this direction. And after dissociation, giving rise to this alternative final product. If we compare also with HBdX and then eliminated HX by the base, and we have palladium 0 as active catalyst. But let us, this is always the same, but let us compare this product to that one. If the system has the opportunity to react to this one and isn't stopped here by the influence of the ligand, then this one should be preferred, since the olefin is in conjugation to the oxygen, and therefore this is thermodynamically favored, clearly thermodynamically favored. I should add that this type of reaction is possible also enantioselectively if you provide chiral ligands and this bidentate ligand with a phosphine and a nitrogen coordination site is suitable for chiral induction in this case. Some variants and applications of the Heck reaction, especially interesting, are intramolecular Heck reactions. An olefin is offered intramolecularly to a vinyl bromide. Again, palladium catalyst and base, always the same. So, what will happen? First step you should have in mind is the oxidative addition step, forming that vinyl palladium bromide. It will coordinate intramolecularly to the olefin. Then a carbopalladation will occur, and somewhat selective a 5-membered ring is formed in this case. That means it is, according to the Baldwin classification, a 5-exotric cyclization, which is preferred to the 6-endotric process. Let's have a look what the competing 6-endotric process would deliver. Is that. So, as I said, this is a minor competing process in general. Beta hydride elimination. Will lead to this type of complex first with the hydropalladium bromide still coordinated to the olefin. If it dissociates, then you would get to this diene, and in this case, with the R groups symbolizing a fluorine ring system, it indeed nicely worked. 84% have been obtained, and the reaction conditions were potassium carbonate as a base, tetrakis, triphenyl, phosphine, palladium as the catalyst or the pre-catalyst, and acetonitrile as the solvent. However, in this type of reactions, you should always keep in mind that as a competing reaction, a readdition could take place. A readdition with opposite regio selectivity. And now we have an eta-1 palladium allyl complex, which can stabilize itself by an isomerization to a clearly more stable eta-3 palladium complex. And indeed, once we had the case in the own research group that, to our surprise, a similar allyl palladium complex even survived a column chromatography through silica gel. So, and if these complexes are under certain reaction conditions so stable, then it's clear that these trap are a palladium and therefore catalyst trap. And that might be the reason why you need somewhat, well, 10% catalyst loading for reactions like that. However, these reactions are interesting. A diene in a schizoid conformation bound into a schizoid conformation, nicely set up for additional Diels-Alder reactions, can be very useful in organic synthesis. Another nice example of surprising things that can happen within palladium catalyzed reactions, again Heck-type reactions, R in this case was a sulfone group. A sulfone amide was the substrate. Reaction conditions: palladium acetate, 5 or 10% were applied. For the Heck reaction, Heck-type reaction to occur, clearly reduced than in situ. Potassium acetate as a base and anisole as solvent, 150 degrees, 18 hours reaction time. Well, first step, oxidative addition here to this position, and then again, just in the case we studied before, a 5-exotric cyclization as the preferred next step. So, mechanistically, what could be the next step? We don't have a hydrogen in better position. So, we could have the retro process, since also the carbopalladation is somewhat reversible. But in close proximity to that electrophilic palladium-2, we have an electron-rich olefin, and an interaction will occur. Somewhat surprising, but working very well. Again, a carbopalladation occurs at that olefin. So where will we get the CC bond formation? To this position would be a 4-endotric cyclization or a strained cyclopropane formed by a 3-exotric cyclization. And indeed, the latter one is preferred. this should be the next intermediate, and now we have in the periplanar position a hydrogen, the beta hydride elimination occurs. And let's do the formation of the final product. This one, which has been isolated in a very nice 78% yield. Another example which too is a case of a selectivity process, selectivity problem, selectivity between exo and endo trig cyclization. In this case, we get the 7-exo trig product as the main one, 75% yield, and the 8-endo trig also occurs in a 6% yield. And just as a really easy exercise, please draw the 7-exo trig product and the 8-endo trig product. The 7-exo trig process, of course, forms a 7-membered ring. So 1, 2, 3, 4, 5, 6, 7. Exocyclic with palladium, beta hydride elimination. This is the product, and the 8-endo trig cyclization then sets up 8-membered lactone with this result. Next example, here we have a highly functionalized substrate So this cyclopentene moiety, how is this synthesized? Well, certainly starting with cyclopentadiene and oxygen, then rose Bengal for setting up the right reaction conditions for a photochemical process where we get to singlet oxygen, which then undergoes a Diels-Alder reaction with that diene system, getting to such an endo peroxide, and with the right reducing agent we then get to this diol with the two hydroxyl groups on the same side of a ring. Later on in the semester, within the discussion of the synthesis of allosa mitzolene by Barry Trost and David van Ranken, we will discuss a similar reaction. Such a process is one key step. So, but here, the Heck reaction, we have again the palladium catalyst and the base, and in some excess an alpha beta unsaturated ketone with that side chain. Now we can speculate what will happen. What did chemists have in mind when setting that up? Well, so what will happen? Palladium 0, oxidative addition. So it could then react in a Heck-type process with this additional reagent, but this is then an intermolecular process, and of course the chances are better that the intramolecular carbopalladation will be preferred, since it's simply faster. The intramolecular carbopalladation of that olefin which is already in close proximity to the palladium 2, aryl palladium 2 intermediate. Stereoselectivity in this case, well, let us assume that the carbopalladation will take place on the same side of the ring where it is already located. So, the oxygen behind the blackboard, so the carbopalladation should occur also behind the blackboard in this scheme. So, let us draw the intermediate just here. Right. So, this should be the intermediate, and this can't complete the Heck process with the beta hydride elimination because there is no syn periplanar beta hydride. So the palladium is sitting there just waiting for the opportunity to react with a reagent. Yeah, well, we have that reagent. Now the intermolecular Heck reaction could occur, and well, then it should be clear what is the final product. This one. Simple Heck process with this olefin. Well, highly functionalized. That generally means lots of opportunities for competing reactions, diminishing the final yield, but nevertheless 45% isolated yield for this process. Well, you would be happy about this result. A last example for today. As an exercise. Heck reaction with this substrate, so palladium catalyst and a base. Please guess what will be the product. I'm sure we can skip the first step, the oxidative addition of the palladium here. So we have then an aryl palladium halide. Intramolecularly we have an olefin. A carbopalladation will occur. First of all, let us just count the positions. 1, 2, 3, 4, 5, 6. A 6-membered ring will be formed, of course preferred to a 7-membered ring to this position. 6-membered will be preferred. So let us draw a 6-membered ring. We have a CH2 group here, means there is a CH2 group. Let's mark that. And therefore, we have the next 6-membered ring here. So, this position has been connected to that aryl position. Since well, one could guess which one is preferred, a transfusion or a cisfusion. I would just guess that also in this case it is a cis-fused system. So the attack of the aryl palladium should be from the same side of the ring where it is bound to. Okay, so here is the carbopalladation, and then those 3 substituents are all on the same side of that cyclohexane moiety. This hydrogen is translocated with palladium, and here we have a syn one and a trans one, and therefore the beta hydride elimination will occur here and form the double bond in this position. And this should be then, well, the racemic product, if we started, of course, with a racemic one, if we start with one enantiomer, we would also get one enantiomer here. So in the next session, next Tuesday, we will discuss a lot more of these examples to illustrate applications of palladium catalysis, Heck-type reactions in synthesis. Thank you for listening, and have a nice Easter holiday.